I will be explaining what is the meaning of drift of electrons, why electrons drift, and what is drift velocity. I will also explain how to derive the expression for the drift velocity of electrons in a conductor, and after that I will show a method of derivation which is quite popular in YouTube, but it is wrong. There are delocalized electrons in a metal. Delocalized means that these electrons do not belong to a single atom. So they are free to move between different atoms. That's why they are also called as free electrons. When a potential difference is applied across the ends of a metallic conductor, then electricity is conducted, that is, a current flows in the conductor due to the motion of these free electrons. That's why these free electrons are also called as conduction electrons. In the absence of an applied electric field, these free electrons move completely randomly. Therefore, their average velocity is zero. But when a potential difference is applied, such as by connecting a battery across the ends of a metallic conductor, then there is an electric field. This electric field exerts electric force on the electrons. So, these free electrons are accelerated. Since electrons are negatively charged, their acceleration is opposite to the direction of the electric field. Now also, these electrons move in different directions with different velocities. As they move, they collide with positive ions, but due to the electric field, they have a net drift opposite to the electric field. Current flows in the conductor due to this drift of electrons. With this, we come to the definition of drift velocity. The drift velocity of electrons in a conductor is defined as the average velocity of free electrons in the conductor in the presence of an electric field. Next, we will see how to derive the expression for drift velocity. We make an assumption. The assumption is that when a conduction electron collides with an ion, then the velocity of the electron immediately after the collision is completely random. Suppose that tau is the average time between two successive collisions of conduction electrons with ions. Tau prime is the average time between previous collisions of conduction electrons with ions and an arbitrary time instant. Tau double prime is the average time between the arbitrary time instant to next collisions of conduction electrons with ions. You can choose any arbitrary time instant at which you want to find drift velocity. The force on a conduction electron equals the charge on an electron multiplied by electric field, where the charge on an electron is negative E. By Newton's second law, the acceleration of a conduction electron A equals F by m, where F is the force on a conduction electron and m is the mass of a conduction electron. So A equals negative small e into capital E divided by m. For the ith conduction electron, suppose Ti is the time interval between the most recent collision and an arbitrary instant at which we want to find the drift velocity. Ui is the velocity of the conduction electron immediately after the most recent collision, and Vi is the velocity of the conduction electron at the arbitrary instant. Vi equals Ui plus ATi. By definition, drift velocity Vd equals average of Vi. Since A is the same for all conduction electrons, therefore Vd equals average of Ui plus A into average of Ti. But average of Ui is 0 because Ui values are completely random, and average of Ti is tau prime as we have used the symbol. Therefore, Vd equals A into tau prime, or substitute the value of A, you will get Vd equals negative small e into capital E, which is the electric field, into tau prime divided by m, which is the mass of the electron. From this, you can find the magnitude of drift velocity. Next, we will prove that tau prime equals tau double prime. As we have used the symbols, tau prime is the average time interval between the most recent collision of conduction electrons with ions and the arbitrary time instant at which we want to find the drift velocity. Tau double prime is the average time interval between the arbitrary time instant and the next collisions of conduction electrons with ions. For the ith conduction electron, suppose Ti prime is the time interval between the most recent collision of the electron with an ion and the arbitrary instant, and Ti double prime is the time interval between the arbitrary instant and the next collision of the electron with an ion. The probability that Ti prime is less than Ti double prime is equal to the probability that Ti prime is greater than Ti double prime. Therefore, average value of Ti prime is equal to the average value of Ti double prime. Or since the average of Ti prime is tau prime and average of Ti double prime is tau double prime, therefore tau prime equals tau double prime. Next, we will prove that tau double prime equals tau. Suppose n0 is the number of conduction electrons at time 0, n is the number of conduction electrons that do not collide with ions till time t, n plus dn is the number of conduction electrons that do not collide with ions till time t plus dt. As you can see, n plus dn will be less than n. This is because some electrons would have collided with ions during the interval dt. The number of conduction electrons which will collide with ions during the time dt is n dt by tau. Therefore, n plus dn equals n minus n dt by tau. Subtract n from both sides. We get dn equals minus n dt by tau. Call this equation 1. Or dn by n equals minus dt by tau. Integrate both sides. On the left side, I took lower limit as n0 because at time 0, n equals n0. And upper limit as n because at time t, n equals n. Similarly, on the right hand side, I have integrated from 0 to t. Find the integrals and keep simplifying. Finally, you will get n equals n0 into e to the power minus t by tau. Call this equation 2. I have written equation 1 and equation 2 here again because you need them. If we take the arbitrary time instant as 0, then tau double prime equals integral t dn divided by integral dn. We use equation 1 for dn and then we use equation 2 for n. The lower limit is 0 in the numerator and n0 in the denominator because n is n0 at time 0. The upper limit is infinity in the numerator and 0 in the denominator because, as equation 2 shows, when t approaches infinity, then n approaches 0. The integral in the denominator equals 0 minus n0, that is negative n0. We cancel negative n0 in the numerator and negative n0 in the denominator. If you find the integral, you will see that tau double prime equals 1 by tau into tau squared, or tau double prime equals tau. We proved tau prime equals tau double prime, and then we proved tau double prime equals tau. Therefore, tau prime equals tau. We found the expression for drift velocity in terms of tau prime. Since tau prime equals tau, Therefore, now we have the equation for drift velocity in terms of tau, where tau is the average time interval between two successive collisions of a conduction electron with ions. Now I will show a method of derivation of drift velocity which is quite popular on YouTube, but it is wrong. This is the method. Suppose that u1, u2, u3 and so on till un are the velocities of free electrons just after one set of collisions. v1, v2 and so on till vn are the velocities of free electrons just before next set of collisions. t1, t2 and so on till tn are the time intervals for free electrons between the two collisions. So, v1 will equal u1 plus at1, v2 equals u2 plus at2 and so on till vn equals un plus atn. Drift velocity vd will be the average of v1, v2 and so on till vn. Since A is the same for all free electrons, so therefore Vd equals average of U values plus A into average of time intervals. But the average of U values is 0 because the U values are completely random and the average of time intervals is tau. Therefore Vd equals A into tau. We substitute the expression for acceleration and we find Vd in terms of tau, where tau is the average time between successive collisions of free electrons with ions. As you can see, we get correct result, but the method of derivation is wrong. This is why the method is wrong. One mistake is that this method finds average of velocities of free electrons just before collision, but the formula for drift velocity should be for any instant. Another mistake is that not all free electrons collide with ions at the same time. So this method finds velocities of free electrons at different times and then takes their average. This is a wrong approach because we need to consider velocities of free electrons at the same instant and then take their average.